Hey folks, welcome to our pre-class video. For this, we're going to be trying to understand a little bit more about kinetics. Specifically, we're going to be looking at trying to learn how to express rates of reactions in terms of the changes of concentration of reactants and products. Hopefully you've already done the screencast, so you have a sense of how chemical rates will change as we change things. But this is just a little bit of the information we need to be able to do stuff in class. And it's a lot easier to do here rather than you guys listening to me just drone on a little bit during class. Now, one of the things I want to point out is part of the reason that we're really studying chemical kinetics is it allows us to be able to address some really important questions. Things like how quickly does a reaction actually happen, what kinds of things impact the rate of a reaction, and how can we actually predict how reactions will proceed. And so you guys have already started to work on what impacts rates of reactions through the screencast, so you're probably already starting to have some answers there. But also, those other ones we'll get to throughout the next couple of sessions of class here. Now, if we look at some data from a reaction, often we'll see something that looks like this. Here we've got a reactant that's in purple, and we can see that this over time is going down. Again, you've seen similar things in the screencast, and then our product is going up. And so we can collect data that gives us a sense of what's happening, but we might want to talk about, well, what's actually the rate of the reaction? And like other things, if we talk about a rate, it's amount of change over time usually. And so we can define the reaction in terms of the progress of, or the change of, the purple reactant. And so over time this is going to go down, so we can look at the change of concentration of the purple stuff divided by the change of time. Now, of course, the purple is going down, right? It's a reactant, it's getting used up. But we often would probably want our rate to be a positive number. So that's where we get this little negative right here. Because that's just kind of important to keep track of, because we want our rates to be positive, much like speed and stuff like that. We could have also, though, defined this in terms of the amount of product that was formed. And so we could look at the change in the amount of green stuff that we had formed over time, the change in green stuff and divide it by the change in time. And so we always really do want that positive rate. So again, just a reminder that we need to have a negative sign that ends up in front of reactants if we're talking about it that way. So let's look at a specific reaction here. Here we've got two molecules of HI that react to form H2 and I2. So we can look at the data for this particular reaction in tabular form. And so we have that over here. And so we can see over time the concentration of HI goes down. That's good. It's a reactant. That's what we expect will happen. And over on the right side here, we see the concentration of H2 and I2. That's going to increase over time. Their product, that makes sense. They're increasing in lockstep. Well, and that, of course, makes sense too, right? Because they're being formed in a 1-to-1 ratio. And so we're in great shape here. Our data looks pretty good. And so now we can think about, well, what happens between 0 and 50 seconds? Let's focus in on that time period. And what we see is from that time period, we can actually calculate the rate of formation or the rate of the reaction for each of these things. And so the rate of the reaction is going to be the change in concentration of I2 divided by time. So we look at final minus initial here, and we figure out, that's 0.0142. We're going to divide that by the change in time, which is 50 seconds, and we can get our answer here. We can do that the same thing for the H2 and the HI, and we get values for each of these. Now, of course, what you might be looking at is going, well, shouldn't these things actually be consistent, right? This is the rate of a single reaction. It shouldn't matter how we determine it. And you're exactly right? All these things should be the same. So if we look at these numbers, what we see is that the HI is actually disappearing at twice the rate of H2 and I2 are being formed. And of course that makes sense, right? If we look at our reaction and our stoichiometry here, we've got two molecules of HI. Those are getting used up, and we're only forming one of each of those other two. So again, we should have a 2-to-1 ratio, so it's not surprising that the change is twice as fast. That's what we should expect, right? And so we want to account for that. We also obviously recognize that this one's negative if we just do a change in concentration. And of course, we want our rate of our reaction to be positive, as we previously mentioned. And so the way that we can do that is we can create a kind of formality of how we're actually going to represent these. So we're going to say the rate is going to be equal to the change in concentration of I2 divided by change in time, or it could be the change of concentration of H2 divided by the change in time, or this negative 1/2, the concentration of HI divided by time. And part of the reason that we want to use, again, that 1/2 is because we've got 2 here, right? So that number is numerically twice as large as the other ones. And so if we think about a general way to look at this, let's imagine we have a reaction of A molecules of A reacting with B molecules of B. Well, we can define this in terms of A. So the rate of our reaction, we're going to say it's going to be negative, because again, A is a reactant, so we'd expect that to go down. We want a positive number, so we're going to put that negative sign. And then we're going to take 1 divided by whatever its coefficient is. So 1 over small a times the change in concentration of A divided by the change in time. And then we can do the same thing for B, right? So it's going to be negative 1 over B, change in B over change in time. Or we could do that with C, so 1 over C times the change of concentration of C divided by time, or the same thing with D. And what you see with all these is if we actually then look at the units for a rate, it's always going to be the amount divided by time. Again, and if we think about something like speed, which is another place where we often deal with rates, right, that would be distance divided by time. Here we're talking about usually something like molarity per minute or molarity per second, or if we're talking about gases, we might have something like atmospheres per hour. So again, whatever unit of time makes sense for the scale that we're looking at, whatever sort of unit that we have that's going to be some measure of amount up in that numerator, that's what we should be looking for. So let me just give you sort of one practice one to shoot for. So here we've got a reaction between H2S and O2. And what I want you to do is go through and select all of the different ones that actually make sense and are a real evaluation of the rate of the reaction in terms of how we talk about it in chemistry. Answer that on D2L and you should be all set for the pre-class stuff.